So, hello everyone. And I see there's a lot of people who were also at the talk at ETAPS that I gave. This talk is based, but it's a little bit of an extended version of it on that one. So forgive me for all the punchlines that you already heard and grant about. So just quickly, as discussed before, we are a small group, so I'm happy to take any questions just during any moment of the talk. And this is precisely why I'm here in this group, more for the conversation than for the marketing pitch. But also one thing that I've observed is particularly around the Ferrocene project, that we need to talk a little bit about what it is and where it is useful and where we position ourselves. And also where there's opportunities, for example, for your projects. Just quickly, I'm Florian. I guess most of you know me through my work in the community and the core team. I'm a co-founder of First Systems and Critical Section. And one thing that I would like to highlight here is we're pretty often nowadays a company that acts as a venture partner on larger endeavors in the Rust ecosystem, where we're a little bit trying to organize things between multiple parties to get value out of this. So be a little bit of a neutral player in this space. And also to be clear about the Ferrocene project, you may have seen the announcement. It is now a joint venture between First Systems and Ada Core. And particularly, First Systems brings the Rust experience. Ada Core brings a lot of experience in compiler verification and also in formal verification. Daniel, I see you raise your hand. Do you have a question?
Just a quick note to the organizers. Several members of our team are having trouble logging in. They're having trouble with the passcode, and I don't know that maybe other people may be having the same problem. So just wanted to let you know that people are trying to log in but having trouble.
Okay.
Sorry for interrupting.
No problem. Okay. So this relationship now exists. So if you see Ada Core people or around this endeavor as well, don't be surprised. So, so what is Ferrocene? And that has actually been also a little bit of a question, as with every new product for ourselves, particularly of that scope. So what the Ferrocene effort is currently, Ferrocene is qualifying the Rust compiler to the highest level of assurances if, for example, certain standards require a compiler qualification. And currently, we are working on ISO 26262 ASLD automotive, though I'll be clear, this is because of customer demand. We have early partners, which I cannot disclose yet, which are particularly interested in that. And that also informs a little bit of how we're factoring our project. It intends to build a modern toolchain component for highly secure Rust. I'll come to what I mean by toolchain component in a second. It is an unmodified Rust C front end plus additional targets and architectures. It may be that at some points we need to modify the Rust C front end because we need certain things fixed, but we are clearly committed to, for example, upstreaming all of these kind of changes. The additional targets architectures comes from the fact that the spaces that we're moving into are actually a space where there's a lot of closed source niche operating systems, and that manages. And we've already, from my time when we were in I did a lot of the licensing legal compliance for the Rust project, and I know the pain of an open source project actually carrying closed source targets. So in these cases, we might close sources, but that is on the demand of the operating system vendor. It is a managed quality product for spaces that need one. Managed quality means, it doesn't necessarily mean that Rust C is like of poor quality. It's more managed quality means is we can directly document to our customers where the quality comes from, what the procedures are, and particularly if we see any kind of defects, actively inform them. So that's the guarantee. It's less of a just because there's a stamp on it, this component suddenly gets better, I could share that a lot of the, for example, the ISO 26262 qualification is actually people looking at your organization and saying, do you have processes in place that if you find a bug that could impact your customers, you can directly notify them and make sure that they can find out if they're actually impacted by this. So, sorry for repeating that joke. When we're talking about safety critical Rust, this is the list of commercial planes that I know that are flying with Rust that I'm aware of. The picture, when we're talking about cars, is similar. That would be an empty road. But why is Rust suddenly becoming interesting and safety critical? So why now? And I think there's a couple of factors. We're currently seeing a reinvestigation of programming practices. The biggest news item I've seen in April 5th, the US Navy has mentioned in a public statement that they have primarily seen software security and safety as a compliance concern in the past. And they think that was wrong, because just delivering the paperwork does not necessarily mean that your program is correct. They are looking closer at the practices that they are being used in-house and at other places. That means they're looking at all of their tools, the programming languages in use. The second is, counterintuitively, systems are becoming smaller again. And a number of safety features that, for example, Rust provides are something that you would mitigate in parts of through your base operating system that you would use, or statically checking your C code. The very short and tangible example around that is our cars are becoming more technical. We have sensors in every component of the car now. Now imagine your front bumper having 5 sensors in it. You bump into another car. In this case, usually the whole front bumper is replaced. So the cheaper your small sensor components become, the cheaper the front bumper becomes. And that interestingly leads to a drift where systems are becoming smaller again. And so what does it mean that we're qualifying for that space? I researched that quickly today for this talk. If I find another good sample for what does it mean qualifying versus certification, and I found this little gem in that, well, there's a difference. Everyone agrees that there's a difference, that the difference is important, but we have no clear definition. So this is like everywhere in IT, there's terms, they're different, but no one really agrees on what the terms mean. But in general, one of the broad agreements here is qualification is often used for tools. So is this tool well understood enough to produce safe results? I always take the picture of a hammer is a good tool to put a nail in the wall. You shouldn't use a screwdriver. That's qualification. And certification is, in the end, did I actually use the right nail at the right place in the wall? And does it do what it should? And does it hold the picture? So certification is often like the bigger form. And the standards are pretty free on which activities and arguments you make. So they're like, give me a good case on why your tool is fitting. Give me a good case on why your tool actually, or the software that you built using this tool actually works. And some standards don't even care about the tool qualification that much. For example, in aerospace, you generally consider the compiler broken. And so they put a lot more emphasis on, does the final binary actually work, and how do you make sure that you test it? But in any case, this is all about collecting arguments and data, and everything that feeds into this and is a relevant argument towards this software is safe. The compiler is of good quality, it is well understood, it gives good error messages. All of this helps on the path of we're actually building safe software. So we actually have a lot of space in how we can, what we can do to fix these things. So apply to Rust C here. That means qualification of the Rust compiler can be done in a black box manner. So given source X implementing requirements, I can check that by reading and by documenting what the source does. Throw it into the compiler. Does it compile down to a binary that exposes this required behavior? That assumes that I have a requirement document available and that I do have a document available that says these tests, test these requirements. And so I can completely treat the compiler as a black box. And that means that particularly everything that we've been talking about, like mir and all the internals, are out of scope for this. But it can be helpful to better understand the compiler, particularly to identify bugs or to build further tooling. And also this hinges on the compiler has relatively straightforward behavior. For example, compared to, let's talk about an async runtime that has highly temporal behavior with and all kinds of dangerous conditions that may happen only in niche cases. And in general, for that reason, libraries and runtime components need certification. So because they will end up in the final binary. That is one perspective, and like a very rough perspective on these things. So current hard gaps that we're aware of in this process is there's no requirement document for the compiler. The reference is incomplete. There's bits everywhere. But particularly, there's also no structured test suite. The Rust compiler actually has very good test coverage. But the question is, which requirements are tested by these tests? Are they specific on an architecture? Are they, for example, specific tests for ARM? In all of this, like, what is this test even there for? Why was it built? What does it test? And is this test sufficient to test all of that behavior? That's the big question. But the other part is also no structured guidance. This is usually called safety manuals or just a coding guideline. And particularly coding guidelines in context of relevant standards. The one I would like to mention here is particularly DO178C, because the avionics standard, the modern one, has supplements that tell you about what you need to ensure to make dynamic memory allocation safe. And that's actually a very pragmatic checklist on what a Rust allocator and what a Rust type that interacts with allocation should ensure. So looking at these standards can be helpful, even if you're not thinking about putting Rust on a plane, because they may have checklists and guidances for things that are of high value to address with additional tooling, or even see if Rust completely addresses these concerns. And the last thing is, there's no organization to provide long-term support, and particularly that is approachable for these kinds of concerns. And that's the thing where we see Ferrocene. That's pretty vague, but it's a space where no use actually exists. So needs to remain vague to a point, because we're going to figure out how Rust is going to be used in those settings, in which parts exactly, on which terms. Support for a compiler in those spaces can go up to 60 years. That's certainly not something that the Rust upstream project is going to provide. Or if not, or if it does, all kudos there. So there's surprisingly little that should concern you as like formal methods, from a formal methods perspective. There's a couple of things we moved away from for now from our public communication. We had a lot of early communication that was talking about looking closely at mir and trying to, for example, express the language as a mapping between source code and mir, and then further verify compiler components. And the reason why we did that is actually very blunt. First of all, we couldn't find partners for it. It has an organizational drag on the Rust project itself, because you need to work on these components and enable certain things on these components. And the other part is actually directly finding people that want to have a qualified Rust compiler now at a predictable time frame. Going to check the chat if there's any questions in it, or that's okay. No, they're not for me, or already answered. So where's the state of Ferrocene? The state of Ferrocene is that we've actually found ways to order the work pretty directly we work on the compiler, we get the compiler qualified, and that's even without Libcore. As I said before, Libcore is something that ends up in the final system that can be certified through all manner of means. Like, it's totally okay if you use a uncertified Libcore and you build a system and you can make 100% sure that for all inputs, it presents the expected output. Then you don't need a pre-qualified component or something, because if you can present that the system works, that's okay. So that's the first step that we want to unlock. People that want this compiler and that want a compiler with support shipped and a good understanding what that compiler does. And then we would move on to Libcore and start certifying these things. Every time you do this work, so basically your customer can do that work if they want to, but the usefulness of a central company doing that is just that, well, it shares the work, and you don't need to duplicate that. So the compiler, as I said before, is feasible to be qualified in its current state. And contrary to the previous communication, we chose the straightforward path. We write down requirements and we test those requirements using classic testing first. That does not at all rule out adding further methods. Everything that improves the trust and the stability of the Rust compiler is definitely very well welcome. And the current state is that we're roughly 50% done on requirements, and we're currently working on categorizing tests. And the strategy that we have from the Ferrocene side is that we are coming from the front end. The hardware design space is others. There are a lot of companies around that, for example, build compilers for specific targets, specific hardware architectures. That is not quite the direction that we're coming out of. We're looking at how we can unlock these kinds of architectures. That is actually quite feasible, as a lot of these vendors nowadays use LLVM. So that could come through collaborating with one of these vendors and using their LLM fork as a backend. But to start unlocking the existing tooling for users, Rust-C, Clippy, etc. Already a lot of Clippy lints, for example, implemented a lot of things that are needed for that space for helping people out. And then write new tools where needed. Supply chain safety is a huge topic in that area currently. So how do we even figure out where the code that we compiled came from, and who's responsible? So a huge part of this requirement specification is, of this requirement stock, is something that's basically akin to a spec. And for lack of a better term, we're actually calling it the Ferrocene spec. So we're working on a Rust-C specification as the basis for our requirements engineering. It's based on the structures of the value and the values of the ADA specification. And this is one of the parts where, for example, we're collaborating very closely with ADA Core. And we are seeking feedback and contribution here on a high intensity basis. We're happy to currently give access, and we will later open it to general audiences. Happy to work with students, all of these kind of things, but it is something that we currently need to deliver our promises to our customers by the end of the year. That's kind of the scope that it's in. And also, most importantly, it makes no claim of being the Rust specification. The most important bit here is it is writing down how the current Rust-C behaves. It's not meant for any kind of language evolution, discussing language evolution. So in contrast to classic language specification, if the compiler does X and the specification says Y, the specification is wrong. We are currently using this to have a structured write down of our understanding of what the compiler does, to also provide tests there. So just to give you a little bit of an insight on how qualification testing looks like. First of all, you take the combination of all of your requirements. So for example, the language version as defined in the specification, your architecture and your target. So for example, ARM v7 Linux, and all of the core libraries that are definitely needed for running a program. And what is being tested are all of these as a configuration. So imagine a big test matrix, but the test matrix goes down to the detail of this is the compiler version, this is the architecture in use on that processor architecture with this operating system, with the specific operating system version, and all the compiler flags. So even if you say there's two different optimization levels you can use, then we need to run the test suite twice. And all of these kind of things. So this ends up as very thorough testing on a very specific, on a very narrow path. And each of these configurations will become, will be tested, and everything that makes this matrix more organized is good, I can say.
Short question.
Yes.
So where are we compared to, say, C or C++ or your other favorite language?
Yeah, what do you mean by that?
So this standards of certification, has it been done for C or C++?
Oh, sure. This is regularly being, so this is the approach that is being done for C and C++ compilers. So a lot of these tests are run on a regular basis, and definitely before any release, and made sure that those tests are all green on all platforms that are supported to this level. And so we give an example. If you an example for a target that is upstream, that is used on an operating system, that scope is, for example, VxWorks. The upstream Rust-C carries a VxWorks no that Wind River have contributed. And that one upstream is not qualified because no tests have been run, and there's no way to figure out whether it is working as intended and it's actually safe to use. And the important part here is that Wind River at some point, or anyone else, could ship you one specific Wind River operating system version. I'm not sure what version they're currently on. Let's pick a random number, 7.1, plus a specific compiler on top. Someone has a reverb. Okay. So plus a certain compiler on top, and that package is then assumed safe. Or no, it is not assumed safe, sorry. It is assumed qualified for use. You still have to make sure that everything that you put on top of that, everything that you build on it is functionally safe. So for example, all the breaks work and all of these kind of things. And that's a common practice. And these test matrices get big. And especially if, for example, weird hardware is involved, it also becomes quite complex to just build the matrix line there. Does that make sense?
Yeah, it makes sense. And so is C certified for the standards for aviation and automotive that you mentioned before?
Oh, you don't certify languages. You really talk about specific compilers.
Yeah.
So you can
C or C-Lang?
Yeah. You can acquire specific compilers. So, for example, if you look, for example, just at what Ada Core sells you a toolchain with not only Ada but also C, C++, additional tooling, a tool for model-based development, and all of these kind of things. And that's where these vendors usually differentiate.
There's another question from Daniel in the spec. Maybe you want to raise it yourself, Daniel?
So how universal are those specs? So there's a difference between the activities that you do, like, for example, running tests, and what the standards want. So, for example, the ISO 26262 standard is very European, but is generally the activities that are in it are generally accepted by all other authorities. So the road standards in the EU are usually stricter. So what you end up doing is you take the strictest of these, and there's usually a good pathway to resubmit paperwork that says, this is what we're doing to ensure safety here, and submit that to different authorities. So yes, there are different ones. Some of these are global. Some of these are driven by the US, some of these are driven by the EU. The one that is currently driven by the US is probably the most relevant currently, is the one for cybersecurity in vehicles, which I always say it's the please encrypt the connections of your firmware updater standard. And also that's the one that now mandates that you actually need to declare where you got the software from that you're putting in our engines. The universality of those specs is differing depending on which one, which area you're targeting. But in general, when it comes to software, the expectation is thorough testing and documentation and requirement engineering.
Does formal analysis count as testing, or is it really only like traditional testing that counts?
That's a good question. I have a slide on that later. So all of the modern standards do actually recommend formal verification or formal methods through a little bit of the back door. So ISO 26262 ASIL D. So there's 4 safety levels from A to D, and depending on the safety level, there's different requirements on how, for example, you write your requirements. And ASIL D, for example, says your requirements need to be in a semi-formal or a formal language. Semi-formal is UML. That's also okay, but like some kind of structured notation. And the other thing is that you always need to make sure that your tests match the requirements. And the nice thing about formal methods is they also bring the checkability with it. So you're also in some way writing the tests along with it. The problem is that then you end up in a situation that you also need to trust this tool to be correct. So it must also be, in this case, be qualified to the same level of assurances. Does that make sense?
Yeah.
Yeah.
And do you ever get conflicts between the different standards, right? Like if one of them has, for example, the coding standard they employ and it requires different patterns than some other standard would require.
Oh, this is where it's where the standards are deliberately vague. So they say, please present us the structured way in how you write Rust code, which currently doesn't exist. There's no coding standard on how to write high assurances Rust code. But if there's a commonly accepted one, this is what becomes a safety argument. You can say one of our safety arguments is we are following this commonly accepted standard that is recommended by this and this authority. Yeah, and this authority can even be the compiler vendor itself. The more it's in use, so proven in use is part that you can make as an argument. Anything that reasonably builds trust can be tried as an argument, so to say. So it's really like you can take this process as it verbalizes. What assessors want to see is make us the case on why this is safe. We give you certain boundaries and certain recommendations. Yeah. Did that answer your question? So we can, to an extent, pick ourselves, so to say.
Yes, thanks.
You said there's no coding standard. There's a group of people writing high assurance Rust, the online book, I think. Are you involved in that?
No, but I've seen that the author just has joined the call earlier.
Okay, so maybe he can comment on that later.
Yeah, but as far as yeah.
Let's continue with the talk.
Okay. So that was the part on the compiler and the language in itself. The next question is how do we deal with Libcore? And Libcore is actually a little bit of a bigger problem. You may have seen in the picture that I assessed Libcore as more work than the compiler itself. And how does that end up? The reason there being Libcore will end up on in any kind of system that we're using Rust on. So we need to take a much closer look at it. And the problem that Libcore currently has, it unifies roughly 3 concerns. First of all, it has API around primitives, which need compiler knowledge. So Libcore is special. There's some types that just exist that are never defined anywhere, such as primitive numbers, U8, and such. And that's all good. But then it also comes with a library defined types that the compiler has knowledge about and uses, such as the iterator and future traits. That's also fine. But then it also comes with general heapless convenience libraries. And that's hard to write down as a requirement. Like, how is this library factored? Every time, and for example, what do we do with users that don't use these libraries? So then we would have to make clear, okay, during link phase, they're excluded, and then we need to make that argument, and we need to make sure that they're actually excluded, and then they're not used. So dead code costs money in that case. And dead code elimination too, because you need to verify that the dead code elimination, that the dead code is actually dead. And you cannot trust the compiler on this because the compiler is broken. And the last bit is some of these special cases where some people are a little bit frustrated that, for example, Libcore ships a whole UTF-8 implementation just for STR. And this is, I think, this was a good choice when Rust was designed and for the use case that it was designed. But an engine control unit on your car probably doesn't do UTF-8. So the easiest way to get Libcore certified quicker is actually just provide an ability to say, okay, I don't want the convenience libraries, I don't want the UTF-8, and then we can go and say, we'll certify the rest first. And there's the problem that there's no clear management strategy there. I've seen a very clear management strategy for libstd just recently on the Rust blog. And yeah, all of this were easier if the library came in pieces and with feature flags. And this is actually something where our hands are tied because we cannot, without good reason, unilaterally come up with a management strategy from the side of Ferrocene, because this impacts also the scope of everyone who uses Rust in a non-qualified fashion and in its current use cases. So this is something where we think an initiative is needed, and also people to collaborate there and give concerns. A lot of these things are actually also listed, for example, in the Rust in Linux initiative's roadmap issue. So it's not like this is an isolated concern that is only for that kind of space. It is just a concern that we share with a number of other special use case users. And the other bit, and I think that's where it becomes interesting for formal verification and for newer formal verification efforts, there's literally no certified libraries at the moment in that space. And that is interesting because that's a huge chance, because thank you for the question before on those standards. That means we can draw the picture on how are safety arguments made for Rust libraries, what is the tooling that we recommend, what are the standards, given that we're in a space where it's actually feasible to bring out the big hammers and where it's actually cost effective, even in a short run. And there's a window here a little. The SAE, a standards body, has formed a Rust organization studying standards for Rust development in the dollar industry. They're not sure which industry it is yet. Currently it's automotive, but they're also thinking about people like aerospace. This one is led by a couple of crustaceans. I'm part of it, but I'm not part of leadership that have their name in this space. So this is not like in any way a problem, but the process currently can be influenced. It will, at some point in 2 years, it will probably come up with a final document and in between have comments. And the other thing is the next call platform switch is indicated for 2025, and it will contain Rust. I'm aware of a number of places where Rust is being used in those environments. So that means it's now currently a phase in which there's actually an investment into that space. That also means we can set our standards there. And the chance for formal methods here is broken down. High assurances need a traceable flow from requirements to testing. And as I said before, you can you can look it up in ISO 26262.864. The modern standards highly recommend fully formal notations for all safety requirements and are deliberately vague on what you actually use. So you can pick a formalism that suits your needs. But there's, for example, a lot of interesting open questions. So for example, how do we make safety arguments for generic codes? Previously, most generic code used in these environments, particularly in automotive, was C++. And we all know C++ templates are basically fill this in, try to compile it, see if it compiles. So in those environments, no one makes safety arguments for generic code. They roll each of the instances out and then prove the instance. But can we do better if we have a stricter, a stricter type system, or at least exploit that type system to make that work easier? So that's a good question, and I have a short slide on that. But here comes our role in this. The safety argument for every tool also hinges on the safety argument of the specific compiler. So you need to target a compiler version with your tool. This is also the thing that we want to kind of structure at some point, say, absolutely no problem with the Rust project releasing a version every 6 weeks, but also indicating these are the ones that we recommend, for example, for this kind of development. Will that be on a 6-week peak? I don't know. Currently, we're looking at maybe half a year. That's the industry standard. I've seen people who want to accelerate that. So I want to give absolutely no comment on which versions of a compiler will be the qualified ones and which one not. Time will show. So just to explain a little bit about why I find this ORD problem so interesting, because it's like I think it's simple enough to have a discussion. If you have a library that exports a sort function that only expects that all elements of the vector implement ORD, assuming the sorting algorithm is correct, every instantiation of that sorting function could be incorrect depending on whether ORD is broken or not. That's no problem. We can, worst case, we could just go through the whole program, look at all instantiations of sort, figuring out what O is, and then checking each of them hand by hand. But the question is, can we do that better? And for example, can we reliably communicate the takeaway that both we're saying the sorting algorithm is correct, and we've done as much as we could, not knowing the context which in it is used. The usual term, ISO 26262 names this safety element out of context. So you need to make the argument without knowing what the end context of the usage is. So how can we reliably communicate this takeaway and the requirements in a structured fashion? And given that no standard for this exists, that's also an opportunity to say, okay, let's draw that picture. How do libraries communicate to each other that we've done all we could for the safety argument, but there's still a number of gaps that you need to address for making sure that library is safely used. And I think that's an interesting problem to think about. And the interesting part here is that we're operating in a space where we are currently live without legacy. And that is probably the experience that, at least for me, that has been a thing that I've often run into, this kind of, oh, okay, that would be a really clean solution if the world didn't exist. So we're very much at the beginning here. And the thing that I want to say, and this is the pretty interesting thing that we've seen over the last year, this tiny pointer was much outside of that point. Rusty and safety critical isn't here yet, but there's a number of companies that have already said, we are going to use this. So we are at the beginning of this bubble. So we can think about, okay, how do we draw within that bubble, and how do we keep a little bit like as much control as needed as a group, as an environment, that we can make sure that this is actually something that is better than the current status quo. The current status quo is very much understood, and is always a good way to fall back to. If you find no better solution, then the status quo actually does nicely. And there's a lot, given that Rust is systems programming language similar to C and C++, you can go and just say, okay, then let's just qualify it like we qualify a C++ compiler. That's always good. So that's a great place for serious experiments. And I have this little draft for a future library ecosystem. I think one of the things that's interesting, given that we're working on small devices, it is currently possible within that environment to ignore the standard lib as a whole. Parts of it maybe are interesting, but as a whole, no. Because the standard lib also deliberately does not make certain guarantees. For example, vector drop order. That has changed in a couple of Rust versions back, 20 or something like that. But the standard library actually never gave you a guarantee on that. And to be honest, probably some of the places we care about would not like a change of such behavior, even if it's for performance or something like that. Because if you already wrote your tool to be within, or your software to be in the performance bounds that it wanted to be in, you wouldn't care about a performance optimization. Creating a fully formally verified ecosystem will definitely not possible within this. But one of the questions that is currently grinding my gears is like, how do we keep the door open for more and more tools to make sure that our libraries are correct? But one of the things that, for example, could currently be a useful thing is what shapes and forms of libraries are definitely not easy to verify. So basically saying these patterns are cool, but they're hard to in any way write requirements down or in any kind, especially specify or verify. This particularly applies to unsafe operations. Which unsafe operations are good enough, well understood well enough that we do see a chance for making these parts safer, or are there unsafe operations that we should just generally avoid? Because this is actually something we can do. If you're in a qualified environment where you have to follow certain standards, we can just write down in the standard for now, by the way, this pattern is banned. Thank you very much. We don't understand it well enough. And that sounds a little bit like, cool, we can do that, but it's more, this is a common practice to make sure that you keep these kinds of doors open. And that is actually the luxury here, that in those spaces, it is very common to mandate certain practices, and you don't need to deal with the freedom of the whole ecosystem. You don't need to deal with that one. And people actually are searching actively for that kind of guidance, because anything where you say, don't do this, is actually good for an engineer in that space, because that means they don't need to make the hard work of, okay, I have two patterns here, which one actually makes sense? What's my opinion? And where can I find people with experience? So a strategy here is to start small and grow. We start building with small and focused libraries. We have a number of ideas around that. Feel free to send me an email. This starts with specific allocators and things like that. Create small new experience around tooling that does ease making these safety arguments for these libraries. And particularly chipping away from the learnings presented at this group, the one problem that this kind of tooling has is that it needs to be of those levels of assurances that the code the code of under inspection is also be targeting. So probably this is not a good space for research tools, because you want to have a little bit more flexibility into which direction you build that tool, and then continue mapping out the field from there, and solve a number of hard engineering problems along the way, particularly for these tools, support for older Rust versions, stronger backwards guarantees, all of these kind of things. And that's in general a very Rusty way of doing things. And the final thing I want to mention, and that has clarified over the last couple of months, Ferrocene is only a Rust toolchain. We have no intention of entering the toolchain market in general, in that where a toolchain is something that ships you a whole suite of compilers plus an IDE that supports all of these compilers. There's already enough players in that space, and we're talking to those if we can ship the Rust compiler along with that. Rather than that, Ferrocene will remain a project for only focused on Rust. But when we're focusing on Rust, particularly there being an integration process project that will make sure that qualification and certification evidences can be acquired easily and follow a common standard. And that's, I think, the most important bit. That's a question that I always get, is like, how, given that I cannot look at the Ferrocene compiler currently for all of these licensing concerns, what should I prepare for? And the message here is, we are qualifying Rust versions from upstream. So if you use Rust version X, Ferrocene version X should be a drop-in for those that need high assurances and need the qualification and all of these things. Not only that, that's in the interest of tool developers and library authors, because then you can, we don't expect any kind of special casing from, for example, people building formal verifiers. And just to be clear, that keeps the test matrix that we've been talking about from exploding, because any change that we would introduce, again, means more testing. And so a little bit so we see that project more and more as an integrator, where we try to figure out ways how we can make these kind of validation needs happen, and also provide libraries around that. So last thing before we go into open questions, I am a program chair of the High Integrity in Language Technologies workshop held 2022. I'd be more than happy if, for example, a formal Ferris account just tweets that around later. And we'd be more than happy if we receive some papers on the work that you do. This is generally open for all kind of language research. So anything that has to do with high integrity languages like Ada, Agda, what do I know, we're more than interested in, and be happy to read your paper. Thank you.
Thank you. Any questions? Yes, Aysata, do you want to ask the question yourself? Unmute and come on screen.
Okay, sorry, I tried to make the clap, but I actually have questions. So that's perfect. Yeah. So yeah, thanks for the talk, Florian.
Mm-hmm.
Yeah, you mentioned, you know, a $1 industry, then a number of companies and different fields. So I'm still trying to get the grasp on, like, how many are those players going to be?
How many?
Yeah, like how many fields, and then in those fields, how many? I mean, how many industries, and then how many companies are we roughly talking about?
Okay, there's roughly 4 big industries. There's aerospace and defense, which is usually the same, because if you're dealing with aerospace, you're usually also dealing with defense. Automotive. Then there's general industry use, so use in industrial machinery, industrial IoT, for example, is that kind of segment. And then there's medical. So these are the 4 big fields, and there's a number of players around, and there's specific standards to all of those fields, though they are often pretty inspired by each other. So for example, the industry standard has those safety levels, SIL 1 to SIL 4, and they're pretty equivalent to ISO 262, ASIL A to D. Usually what you need at that point is mainly an expert that understands what the specific needs and the specific things that are being addressed in those environments are. For example, I have at some point worked with someone who was in, or talked to someone, not worked with someone, sorry, being in the same town, that worked in explosion security for Siemens. So in industrial settings, some of the machinery needs to be validated that it doesn't catch fire when it explodes, when something around it explodes or something like that. That's not a software concern though. So on the software level, the standards are pretty similar, even if, for example, the standards in why does your system fail are different. So there's always that part. Those are generally encompassing standards that also include software. Yeah.
Okay, and like the train systems.
Oh, yeah.
Automotive, is it automotive? Because I thought automotive was only cars.
Someone's going to hate me if they hear this recording. I always forget railway. There's 5. Yeah, railway.
Okay, that's right. Okay, and then I have a last one, and then I promise I stop. If I'm going to give French examples, sorry. If the French state would buy this certification, like does the French state then distribute to the French SNCF and then I don't know, Airbus, or is it going to be every industry is going to be possible?
It's complete. That's completely up to the nature of the deal, and each of the compiler vendors works with per seat licensing or per project licensing or whatever. So that's that question I cannot answer just for the, like, all of these deals exist out somewhere. Yeah.
Okay, thank you.
Any other questions?
I don't see anyone raising their hand, but Xavier isn't here, and I would hate this not being mentioned. You had this nice board example. So what Xavier has been developing is a general language inspired by the C specification language. He calls it Perlite, and it could be useful too. So it would allow you to specify that the OR trait is actually gives you an ordered set. So it's the language he developed is first order logic with Rust types.
My question is more, how do I publish it, and how do I make sure that people follow it easily? So I mean, having that language is pretty cool, because that's like, let's say, that's less of my interest. Like I take any language I get, so having one around for the sake of an example, or even for an experiment, is precisely what I need, because my personal experiment lies elsewhere. It's like, how do I communicate that, and how do I make sure that I make that usable? So thank you for that. I will definitely get in touch with them.
There are certainly variations possible, but this is at least a concrete language. What we've done is we connected it up with the hexspec language and used it in several backends. This actually worked by Lasse, who's also in the call. So it's quite nicely packaged up, and it can be easily integrated into other projects. So it's at least something to start the discussion from.
Yeah.
Are there any? I see one hand. Let's see who that is. I see a hand on my screen. If you have a
So
question.
I had a question.
Go ahead.
I'm wondering, when you do this kind of qualification or certification, sort of how much is manual versus how much is automatic? And then when, for example, there's a new compiler version, how much can you sort of reuse what you've already done, and how much new work has to happen for every new version?
That's a good question. So the important bit here is that you can, so it's always okay if in the end you end up doing manual testing. So for example, or manual verification. So it is still okay to, for example, compile code and then read it in assembly and see if it's correct there and do that manually. Generally, the testing and all the test runs are automated, obviously, and you try to catch failure there. But what is generally done is that all changes between, so for example, the documentation material and all of these kind of things are manually rechecked. I think, Rob, you have a lot of experience there, or maybe you can add something there. Is Rob still around?
Who, me?
Rod, sorry, not Rob.
Rod, with a D.
I apologize.
So yeah, I'd agree with that. As much automation as you can throw at the problem is what the way to go. And it's a shame there's no one on from I don't think there's anyone here from Adacore. But I mean, if you look at the Adacore builds of GCC, their regression testing, the last time I heard the number, it was something like about 70 configurations get rerun, full qualification, all the testing stuff gets done every night. And that's an awful, that's a lot of effort. It's like, a tier 1 Rust C, qualification run. And yeah, they try and automate as much as they possibly can. Some stuff still has to be checked and, updated by hand. So yeah, and we used to do the same with the Spark toolset. All the proofs that the Spark toolset generated were regenerated and reproved every single day, regardless. And we had a very strict policy about what was allowed and what wasn't. But there was always a bit of mandrolic stuff to actually get a release out the door that was annoying. But yeah, do it as much automation as you can. Would be my advice.
The nice thing about this is that the Rust project upstream already runs practices that are actually pretty much common in that space. So I can share the Rust, the Ferrocene build infrastructure does not use GitHub Actions, but otherwise it's classic BorsNG, and exactly the same as we're doing upstream with some changes to how our process works. So we import every night and check, like we basically import Rust C changes as a patch every night to make sure that they apply on top of all of our targets, to make sure that we catch all of these errors nightly. But it's the amount of effort that had to be done, like structurally on top of the practices that the Rust project already has, was surprisingly little.
Yeah, I think another thing worth noting is that at Adacore, they're also doing all of that on multiple branches of the compiler. They're doing it on the bleeding edge of GCC. They're also doing the last stable release. They're also doing a release they did last year that's got long-term support, and customers are paying for it to still be supported and still have bugs. So they're doing multiple channels on multiple branches for 70 configurations, and at several optimization levels with the compiler and different switches. And that matrix gets really, really big very quickly. You need to be very, very careful about how many axes you allow and how many entries on each axis you're going to have on the matrix, or it does get very, very big very quickly.
It's also fun things. For example, one of the things that I heard is that because it's still practice in that industry to ship libraries as binaries, suddenly changing to a different compiler flag profile for a whole project means talking to all vendors whether they can supply this library with those compiler flags activated. which seems to be a fun exercise that can take multiple months, depending on what your supply chain looks like. But this is also something that we're seeing, those supply chains are also changing. And that's what makes the space much more interesting. I think there's currently a lot of change happening. So it's easy to snipe on the current, but a lot of the companies in that space have also found out that they want to change their practices towards something, I don't want to say more modern, but something that has proven its reliability gains in other sectors. That's the main concern. If you see those industry moving slow, there are definitely players that are deliberately moving slow, but also others that I've heard the term at some point. We always wait 3 to 4 years until the startups in Silicon Valley have found all the critical bugs and everything that makes it crash, and then we adopt it. Which is, I think, if you do that structurally, a reasonable thing to do. Yeah.